Hi all, welcome to Go Classes. In this session, we will we will solve some practice questions from mathematical logic, propositional logic, first order logic. These questions are taken from standard resources, top universities, and we will do the complete analysis of all these questions. Okay? Take your copy pen. Let's solve all these questions together. Don't watch it like a movie. Let's solve all these good quality questions together. I have collected some really good quality questions, some very nice questions from various top universities. Okay, if you want all the questions, all the practice questions, also all the discrete mathematics compact lectures, summary lectures, or I can say compact lectures, and also gate pyqs and practice lectures, then this playlist you can find on the YouTube. On YouTube you can search Go Classes Discrete Mathematics, then this playlist will show. Okay, so this playlist, the link you can find in the description, also in the pinned comment also. But on YouTube you can search Go Classes Discrete Mathematics, and this playlist, Discrete Mathematics Gate pyqs, summary lectures, or I can say compact lectures, revision playlist. So here you can see, for example, Propositional Logic complete summary part 3, Propositional Logic Gate pyq part 1, Propositional Logic Gate pyq part 2, and so on. Okay, so in this playlist you have Discrete Mathematics Gate pyqs, Discrete Mathematics compact lectures, and revision playlist. Okay, now let's start. Let's solve this question from MIT. Question taken from MIT. Given the following statements, three statements are given: P or Q, P implies R, Q implies S. Prove that R or S is entailed. What is the meaning of entailed? Entailed means simply means implied. Okay, so you can say that this word entailed, this is same as implied. This is what it means. Basically, the question is saying that these are the three statements, and we need to prove that R or S, this is implied from these three statements. Okay, so very simple. Remember, entailed, that is same as implied, or I can say inferred. Implied, or I can say inferred. Logically implied. Logically inferred. Okay, so all these words are basically same, logically implied. Now the question is saying these are the premises. From these three statements, prove that R or S can be inferred. So this is a argument based question. Basically these are the premises, this is the conclusion, and we need to prove that using these premises and this conclusion, basically this argument is valid. Okay, means if these three statements are true, then definitely R or S will be true. From these premises we can infer this conclusion. Okay, so very easy question. So what are the premises? You can see the premises are P or Q, this is a premise. P implies R, this is a premise. Q implies S, this is another premise. So these are the three premises. And what is the conclusion? The conclusion is R or S. Okay, and we need to prove that from these premises this conclusion can be inferred, means this whole argument is valid argument. Now to solve this question, there are two methods. Let's see the method number one. Method number one, that is the formal method. What we will do, how to check whether an argument is valid or not? Very simple. What we will do, we will make the conclusion false, then we will try to make all the premises true. If it is possible that all the premises are true and conclusion is false simultaneously, if it happens, then we can say that this argument is invalid. But remember, after making conclusion false, if it is not possible to make all the premises true, then we can say that this argument is valid. Correct? So let's solve this question by method number one. Then we will also see the method number two, that is logical interpretation. Okay, so method number one, that is first step one, that is you make conclusion false. Correct? Okay, make conclusion false. Let's make conclusion false. So to make this conclusion false, R or S, I want to make it false. Then what I need to do? Remember, this is R or S. How to make it false? because this is disjunction. To make it false, I need to make both r comma s false. So you can see there is only one way to make r or s false, that is r also false and s also false, both are false. Okay, so this is the step number 1, you make the conclusion false. Then what is the step number 2? Now try to make all the premises true. Okay, now try to make all premises true. All premises true. Okay, so this is what we need to do. Now we will try to make all the premises true. Already remember r is false, s is false. Okay, so already this r, this is already false, s is already false. Okay, I want to make all the premises true. So tell me how to make this premise true, this second premise, how to make it true? R is false. So can I make P true? I cannot make P true because true implies false. That will be false. I want to make all the premises true. So in this second premise, you can see I have to make P false. Correct? Okay. So very simple. I have to make P false. What about the third premise? How to make the third premise true? Already this S is false. So I have to make Q false, because if I make Q true, then this premise third will become false, but I want to make all the premises true. So you can see this Q, I have to make it false. There is no other choice. Now you can see these two premises, these are true, but I have to try to make all the premises true. So I will try to make the first premise true as well. But you can see P is also false. You can see P is false, Q is false, false or false, that is false. So did you notice that after making the conclusion false, if I try to make all the premises true, that is not possible? Yes or no? So here I can say that it is not possible that conclusion is false and all the premises are true. It is not possible simultaneously. So I can say that this argument is valid. Yes or no? So what is the step number 3? Step number 3 is, you can see argument valid if if step 1 step 2 they are simultaneously not possible. Okay, argument is valid if step 1 step 2 are simultaneously, step 1 and 2 are simultaneously not possible. Simultaneously not possible. Okay, and you can see yes, step 1 and step 2 they are simultaneously not possible. After making the conclusion false, I cannot make all the premises true. So I can say that argument is valid. Okay, so that's it. So finally we have proven that this argument is valid, or I can say that it is a valid argument. Very simple. Okay, so finally I can say that from these three statements, R or S can be entailed, or I can say inferred or implied. Okay, so this is what we have proven. I hope you understood. Let's see method number 2 as well. That is logical interpretation. Without going through this formal method, this is a formal method, right? We are not using any interpretation here. Okay, so you tell me what will be the logical interpretation of this argument, or I can say logically, can you see that this argument is valid? Let's see method number 2. That is logical interpretation. It will give you more intuition. Logical interpretation. So notice one thing. What these premises are saying. These premises are saying that P or Q is true means at least one of them is true. If P is true, then R is true. If Q is true, then S is true. Now, from these premises, we need to see whether we can infer R or S or not. We need to check that from these premises, can we infer R or S? So assume that all these premises are true. Then can I guarantee that conclusion will be true? So let's see, if all the premises are true, then what can you say about R comma S? Let's see. So notice one thing. This premise is saying that P or Q is true means at least one of them is definitely true. Do you agree with me? Either P or Q or both, at least one of them is definitely true. Agree? Okay, yes. So very good. So I can say that from this premise I can say that at least one of them, p comma q, at least one of them is definitely true. Now notice, if at least one of them is definitely true, then at least one of r comma s is definitely true, because the second premise is saying if p is true then r will be true, if q is true then s will be true, and this first premise is saying that p or q at least one of them is true. Now notice, if p is true, then this premise, second premise is saying that if p is true then r will be true. So notice, if p is true then r will be true, if q is true then s will be true, because the third premise is saying that if q is true then s is true. So notice, p or q at least one of them is true, then definitely at least one of r comma s will be true. So I can say that r or s will be true, means at least one of them is definitely true. So that's it, this is the logical interpretation. I hope you understood. Okay, so logically also we can see that if these premises are true, all these premises, if I assume them true, then definitely this conclusion will be true. So I can say that from these premises I can infer, I can imply this conclusion. Okay, very simple. I hope you understood. Okay, so you can notice that p or q, this simply means that at least one of p comma q is true, at least one of p comma q is true. Okay, next you notice, this is saying if p true then r true, if p true then r true, and notice this is saying that if q true then s true, if q true then s true. Okay, so finally I can say that from these three premises I can guarantee that r or s will be true, at least one of r comma s is true. Okay, so that's it, this is the logical interpretation. I hope you understood. So we have solved this question using two methods. Which method did you like more, method 1 or method 2? Let me tell you, method 1 is also very good method, because the chances of error, that is very less. If you use the method number 1, then the chances of mistake, that is very less. But the method 2, this is more efficient, more intuitive, it gives you more insight about the argument, but there is a possibility that you can make a mistake. Okay, so method 2, this is efficient but mistake might be possible, and method 1, this is less efficient but mistake possibility is very less. So both the methods are beautiful, and you should understand both the methods, and then you can decide which method you like more. Okay, now let's move on. Let's solve this question from first order logic, or I can say predicate logic. Question is taken from MIT. This is a beautiful question. Let's solve this question now. So the question is saying, consider the following interpretation of a language with unary predicate, unary predicate p comma q, and binary predicate r. So the universe is 1 2 3 4, only 4 elements in the universe in the domain. P q r, these are the predicates. P comma q, these are unary predicates. R is the binary predicate. Circle the sentences below that hold in that interpretation, means which of these sentences will be true in this interpretation. Okay, now let's see what this question is saying. This is very simple. Universe is 1 2 3 4, so this is the domain. Universe simply means domain. Okay, there is nothing here. We already know universe means domain, or I can say universe of discourse. So this is universe. Now notice one thing. What is the meaning of p equal to 1 comma 3 and and q equal to 2 comma 4 and r equal to this set? What is the meaning? Can you find out the meaning? Let me tell you the meaning. Notice p comma q are unary predicate, means they will take only one variable, means they are defined over one variable. And notice r is binary predicate, means this is defined over two variables. Some students are saying that what this means, p equal to 1 comma 3, what this means, some students are saying that it simply means that p1 is true, p3 is true, p2 p4 these are false. Yes, very good, that is the correct interpretation. Okay, remember one thing, p comma q these are unary predicates. Unary predicates means what? Unary predicate means it's like px qx. Okay, and r is binary predicate. R is a binary predicate. What that means, it means r x comma y. Okay, this is very simple. P comma q are unary predicates, so these are defined over one variable. R is binary predicate, so this is defined over two variables. Now let's see what is the meaning of p equal to 1 3. What this means, this simply means that this predicate p, this is true for element 1 comma 3. Okay, so remember this simply means that p1 is true, p3 is true. Okay, and also remember p p2 is false and p4 is false. This is what it means. I hope you understood. Similarly, what this means, this simply means that q2 is true, q2 is true, q4 true, q1 q3 false. Okay, q1 q3 false. This is what it means. Okay, and let's see what this means. It simply means that, remember, r is binary predicate, so it is defined over two variables. Okay, so you can see what this actually means. Let me write it. This actually means that r, this means r 3 comma 2, that is true. Okay, but notice r2 comma 3 is false. R2 comma 3 is false. Also remember R4 3, that is true. R4 3 is true, but notice R3 4 false. Similarly, for example, what about R11? Can anyone tell me what about R11? Yes, that is also false. Can anyone tell me what about R33? Yes, that is also false. Okay, what about R21? That is true. I hope you understood, and so on. I hope you understood. Okay, so that's it. Now, what we need to do for these sentences, we need to find the truth value. Means we need to circle the sentences which hold in this interpretation. Hold means true. Hold means they are true. They are true. This is what it means. Hold means that they are true. Okay, very simple. So I hope you understood the question. Now that you understood the question, now this is a beautiful question. Let's solve it. Okay. So tell me one by one for all these sentences. You tell me they are true or false. So let's see the first one. The first one is saying for all x, px. Remember the domain is 1, 2, 3, 4 only 4 elements in the domain. So the first sentence is saying that for every element in the domain, p is true. Now tell me, is it true that for every element in the domain, p is true? In the domain, we have 1, 2, 3, 4 these elements, but p is true only for 1, 3. P is false for 2, 4. You can see. So I can say for all elements in the domain, p is true. This is false. Okay, because for all the elements in the domain, p is actually not true. P is true for 1, 3. P is false for 2, 4. So I can say that this will be false. And what is the counter example? Tell me the counter example. What will you say is the counter example? Counter example is you can take x equal to 2. Okay, that's it. Very good. X equal to 2, or you can take x equal to 4. These are the counter examples. X equal to 2 or 4. What about the next second one? There exists x px, means there exists some element in the domain for which p is true. Yes, there exists element. You can see this 1, 3. For these elements, p is true. So there exists some element in the domain for which p is true. Yes, this is true. What is the witness? Who is making this second statement true? Means who is the witness? Who is the witness? Witness means a person who makes something true. Counterexample means a person who makes something false. Witness, who is the witness? I can say x equal to 1 or 3. Please understand. Counterexample means some element which makes a statement false. Witness means some element which makes a statement true. Is this clear? In our lectures, we have already seen what is the meaning of counterexample, what is the meaning of witness. For universal quantifier, we try to find counterexample. For existential quantifier, we try to find witness. Okay, correct? Now let's see the next one, the third one. There exist x, px and qx. First of all, you tell me, what do you think here? Where is the parenthesis? Where is the parenthesis? There exist x. Should I interpret like, should I interpret like this, or should I interpret like this? Tell me what is the correct interpretation here. Let me know. How should I interpret? I should interpret in this way, because please understand, if you interpret in this way, then here this x will become, this x will become what? It will become free variable. Yes or no? It will become free variable. This x will become free variable. And when your expression has free variable, then you cannot find true or false because it is not a proposition. Do you agree with me? In any expression, if there is at least one free variable, then it is not a proposition and we cannot find true or false for it. Correct or not? So now you can see that free variable simply means that here it is not a proposition. Existence of free variable means it is not a proposition, so we cannot find truth value for it. We cannot say it is true or false because it will depend on the free variable, so it is not a proposition. Okay, so remember here that this is the correct interpretation. Okay, now you tell me, this third one, is it true or false? This is saying that there is some element in the domain for which p and q both are true. Okay, px and qx. So tell me, this third statement is saying that there is some element in the domain, for some element p and q is true. P and q is true means both p comma q are true. Is there any element in the domain for which both p comma q are true? No. You can see for 1 comma 3 q is false, for 2 comma 4 p is false. There is no element for which both p comma q are true. Yes or no? So I can say that this is a false. This is actually false, because in the domain whatever element you take, for that p and q will be false. Okay, so I can say that this third statement, this is actually false. Okay, so this third statement, I can say this is actually false. Very simple. Let's see more. So these three we have already seen. Now let's see the fourth one. What about the fourth one? There exists x, px implies qx. Remember, whenever with existential quantifier, whenever you see this implication, then please beware. Means please take care. Okay, so let's see the fourth one. The fourth one is saying there exists x for which if p is true then q is true. Means p implies q. Please notice, existential quantifier will be true if for some element in the domain this internal thing is true. Okay, let's say that this internal thing, let's call it alpha x. For a moment, let's call it alpha x. Now you notice, is there any element in the domain for which this alpha x will be true? Yes, notice one thing, this is implication. So if I make this LHS false, then automatically implication will become true. So is there any element for which P is false? Yes, 2. You can take 2 or 4. For 2 comma 4, this Px, this will become false, and this implication, the whole alpha x will become true. So existential quantifier also will become true. Yes or no? So notice that this fourth one, this is actually true. This is actually true. And who is the witness? Who is the witness for it? Tell me who is the witness. You can take witness equal to 2. Okay, is this clear? Very simple point. Okay, I am just saying that you have, there exists x, px implies qx. Okay, so here if I take x equal to 2, then what will become this p2 implies q2? What it will become? You can see p2 is false. False implies anything. False implies anything that will become true. Okay, this whole thing will become true. So notice one thing, that for this for this element this internal thing is true, and existential quantifier will become true if for some element in the domain this internal thing becomes true. Notice one thing, that 2 comma 4 both are witness. If you take x equal to 2 or if you take x equal to 4, then you can notice this alpha x will become true, so the existential quantifier will become true. Okay, so here this fourth statement, this is actually true. What about the fifth statement? For all x, px implies qx. What this actually means? This actually means that for all x, for everyone, we are saying that if p is true, then q is true. So for every element, I am saying that if p is true, then q is true for that element. So tell me, can I say that for every element, for any element, whatever element you take, if p is true, then q is true for that element? No. You can take 1. For this element 1, you can see that p is true, but q is false. So I can say overall this statement fifth, that is actually false. Okay, who is the counter example? Counter example is 1 comma 3. 1 comma 3 are the counter examples. Okay, so you can see that this fifth statement, this is actually false. And who is the counter example? Counter example is, you can take 1 or 3 as the counter example. Okay, very simple, because for this element 1, p is true but q is false. But the fifth statement is saying that for every element, for any element in the domain, if p is true for that element, then q is true for that element. Okay, but you can see for element 1 comma 3, p is true but q is false. So this statement fifth, that will be false. Okay, so that is false. Okay, what next? Statement sixth, this is saying that for every element in the domain, for all x, if p is true, then q is false. Tell me, this is saying for every element in the domain, if p is true, then q is actually false. So let's see, for every element in the domain you check, if p is true, then q should be false. Notice, p is true for 1 comma 3. For 1 comma 3, q is false. Yes. So this statement is actually true. This statement is true because this is saying that for every element in the domain, if p is true for that element, then q is false for that element. You can see for 1 comma 3, p is true. For 1 comma 3, q is false. So yes, for every element in the domain, if p is true for that element, then q is false for that element. You can check. You can take x equal to 1. For x equal to 1, this will become true. For x equal to 1, this q will become false. So the negation q will become true. True implies true, that will be true. You can take x equal to 2. For x equal to 2, p2 will be false. False implies anything will be true. You can take x equal to 3. For x equal to 3, p3 will be true. q3 will be false. But negation q3 will be true. So you can see true implies true, that will be true. Similarly, if you take x equal to 4, then p4 will be false. False implies anything will be true. Okay, so you can see that this Sixth statement, this is actually true. Okay. Now let's see. What about the seventh statement? Seventh statement is saying for every element in the domain, if Q is true, then P is false. Yes, this is also true. The seventh statement, this is also true because for every element in the domain, you can check that for any element in the domain, you can check that if Q is true, then P is false. You can see for 2, 4, Q is true. For 2, 4, P is false. So yes, this statement is also true. Okay, what about the eighth statement? Eighth statement is saying, let's see the eighth statement. It is saying, for all x, there exists a y, Rx, y. Remember, this is for all there exist. This template we have already seen. For all there exist. For all there exist template. So what is this template? Basically, when we write for all x, there exist y and something here like pxy, what it actually means? It means that for every element in the domain of x, this is the domain of x. So for every element, remember, for every element in the domain of x, and this is the domain of y. So remember, for for everyone there is someone, but remember, for different people there can be different y. For different x there can be different y. Okay, so remember, it's like this, that for everyone there is someone. Like for this we have this, for this we can have this, maybe for this also we have this. Okay, so it's like that for every x there is a y, for everyone there is someone. Different people, different x can have different y or same y. Okay, I hope you are getting the point, that for everyone there is someone. This is the idea, this is the template. For all there exist. So I hope you understood. Very simple, right? Okay, so you can see that for every element in the domain of x, there is some element in the domain of y such that this pxy is true. This pxy is true. Okay, so this is the idea. I hope you understood. Remember, this is also fine. For example, if everyone in the domain of x, if everyone in the domain of x has same y, that is also fine. There is no problem. I am saying that different x can have same y or different y. Okay, so this is also perfectly fine. This is also fine. And remember that this is the domain of x, this is the domain of y. If you have like this is also perfectly fine. This is also fine. I hope you understood. Basically, for everyone there should be someone. Now let's see this eighth. So for all x in the domain of x, remember here the domain of x, domain of y, that is same. One more thing I want to tell you, by default always the domain is same for all the variables. But in the question, if they give you that different variables have different domain, then you have to consider different domains for different variables. Otherwise, by default, for all the variables in any expression, for all the variables, the domain is always same. By default, the domain is same for all the variables. But in the question, if they give you that different variables have different domain, then that we have to consider. So here you can see x and y, they have the same domain. This is the domain of x, this is the domain of y. We are saying that for every x, there is some y such that Rxy is true. So can I say that for every element in the domain of x, there is some element in the domain of y such that Rxy is true? Tell me. This is the domain of x, that is 1, 2, 3, 4. This is the domain of y, 1, 2, 3, 4. Can I say that for everyone here, there is someone here such that this R is true? So let's see. For 1, who is there? You can see for 1, there is no one. Notice one thing. Notice one thing. For 3, there is 2, 1. For 3, there is 2, 1. But for 1, there is no one. For 2 there is 1, for 2 there is 1, for 3 there is 2, for 4 there is 3. But notice there is no one for 1. There is no one for 1 alone. This person. Okay, this person. You can see it's like, if you consider this is like a wedding, then you can see that there is no one for 1. Okay, so you can see. So here you can see that this is basically isolated, or I can say alone, or I can say isolated. Poor person. Okay, poor guy. Okay, so let's see. Poor guy. The point is, now I can say that this eighth statement, this is actually false. Okay, is this clear? Because in the eighth statement, we are saying that for every x, there is some y such that rxy will be true. But here you can see that for this one, there is no one such that r1 comma y will be true. It's like basically here the counter example is x equal to 1. Here the counter example is x equal to 1. Okay, because you can see if I take r1 comma something here, then there is no y such that it will become true. There is no such y. No such y. Okay, so this is the whole point. So finally I can say the eighth statement, that is false. What about the ninth statement? Ninth statement is there exists y for all x rxy. There exists y for all x rxy. Now this is the template there exists for all. There exists for all template. This template also we have studied. This template is like this, that if you have, for example, there exists x for all y pxy, then when can I say this expression will be true? What this expression is basically saying, this is saying there is someone fixed, and with that person every y. Okay, it's like there is someone in the domain of x, there is someone fixed, such that for every element in the domain of y, this pxy will be true. It's, remember, there exists for all y means there is someone such that with that fixed person everyone. Okay, so it's like this, that in the domain of x there is someone fixed. Okay, there is someone fixed. Let's call it a. Let's call it a. Now with this you take everyone in the domain of y. Okay, with this fixed person you take everyone in the domain of y. Now this pay should be true. Is it true? Okay, so very simple point, that there should be at least one person in the domain of x. There should be at least one person. There can be multiple. For example, this b also can have. Okay, but the point is that in the domain of x there should be at least one person, one fixed person, such that with that person you take any element from the domain of y, then this pay should be true. Okay, so this template diagram is like this, a fixed person with everyone. Okay, so the diagram will be like this. Okay, so this diagram, you just understand that there is a fixed person with everyone. This is the diagram. This is the diagram for there exists for all template. Okay, now let's see. So you can see one thing, you take care here, there exists y and this y is here. Okay, you take care one thing here, that there exists y and this y is here. So what I'm saying, you take care of this. Notice here something tricky, that there exists y. If I say there exists y for all x rxy, now Here notice this y is here, this y is here. What actually it means? The same thing, that in the domain of y there is a fixed person, and this is the domain of x. So there is a fixed person, there is a fixed person, such that you take everyone here in the domain of x. This template is fixed. There exist for all template. The template is fixed. But notice one thing, that this y, let's call it a. Okay, this fixed person, let's call it a. Now we are basically saying that r, here this y is here, means this will be r x comma a is true. Okay, understood? Very simple. Now let's see here. So there exists a y. Is there any y such that whatever x I take, this r x y will be true? So this is the domain of y, that is 1 2 3 4. Domain of x is 1 2 3 4. Tell me, for example, can I take one? Will one work? Can I take one with everyone? And can I say that 1 1 r 1 1 r 2 1 r 3 1 r 4 1 are true? Notice r 1 1 is not true. Okay, can I take this 2 and can I say r 1 2 r 2 2 r 3 2 r 4 2 is true? You can see r 2 2 is not true. Can I take 3 and can I say r 1 3 r 2 3 r 3 3 r 4 3 is true? No, you can see r 3 3 is not true. What about 4? Can I take 4 and can I say r 1 4 r 2 4 r 3 4 r 4 4 is true? No, r 4 4 is also not true. Okay, see, very simple. Basically this statement, this is actually false. This is actually false. Did you understand? Because here if I take 1, okay, let's assume I take y equal to 1, then where is the problem? The problem is this 1 1 is not true. Also you can see, yes, 1 1 is not true. Okay, yes or no? The rest, 2 1 is true. 2 1 is true, 4 1 is true, 3 1 is true, but 1 1 is not true. Okay, it's like this, that for this one we have 2 3 4. Okay, but we don't have this. That is the problem. Also notice, with this 2 you can see we can take 3, we can take 4. Okay, with this 2 actually we can take 3 comma 4, and you can see that with this 3 I cannot take anyone, and with this 4 I cannot take anyone. Okay, so that's it. Total we have 6. Yes, so this is the idea. I hope you understood. So the ninth one, this actually will be false. Okay, I hope you understood. Now let's see the next one. What about the 10th one? The 10th one is saying for all x, the 10th, we are discussing the 10th. For all x, px implies there exists y rxy. Okay, so basically this 10th statement is saying that for every element in the domain, if p is true, then there is some y such that rxy will be true. Okay, now notice, for all element in the domain we are saying that if p is true, then this will happen. Now you can notice that universal quantifier will be true if for every element in the domain this internal thing is true. Now you can see this internal thing is true when p is false. So you can take, if I take x equal to 2 comma 4, if I take these two elements, please understand, if I take these two elements 2 comma 4, then the internal thing will be true. So I only have to check 1 comma 3, because for 1 comma 3 p is true, for 1 comma 3 p is true, then for 1 comma 3 I have to check if there exists a y such that rxy is true or not. Okay, so let's see. Notice, let's call this whole thing for a moment. Let me call this entire thing, let me call this alpha x, alpha alpha. Let me simply call it alpha. Okay, I am simply calling it alpha. This internal thing, I am simply calling it alpha. Now you tell me, outside we have universal quantifier. So tell me, universal quantifier will be true if for every element in the domain this alpha is true. So you tell me, in the domain we have these elements 1 2 3 4. So tell me, if I take this alpha, if I take x equal to 1, then what about alpha? If I take x equal to 2, for example, if I take x equal to 2, if I take x equal to 4, then alpha will be true. Then alpha will be true. Why? What is the reason? Because this p will be false. False implies anything will be true. Yes or no? Okay. What about x equal to 1? If I take x equal to 1, then p will be true. Now, is there any y such that r1 comma y is true? R1 comma y is true? No. Did you notice that this x equal to 1 is the counterexample here? For this 10th statement, this is actually false. This 10th statement is actually false. And who is the counterexample here? Who is the counterexample here? Counterexample is x equal to 1, because focus. If I take x equal to 1, for this element, if I check, let's check for this element, then p is true for this element. Okay, if this is true, then this must be true, means there should exist a y such that r1 comma y must be true. But there is no y such that r1 comma y is true. Whatever y I take, you can notice that r1 comma y is not true. So this actually will be false. So true implies false is equal to false. So I hope you understood that the 10th statement is false and the counterexample is x equal to 1. What about x equal to 3? If I take x equal to 3, then this p3 will be true. Is there any y such that r3y will be true? Yes, you can take y equal to 2. Okay, here actually you can take y equal to 2. Alpha will become true by taking y equal to 2. Okay, but here there is a problem. No such y. Alpha will be false because no such y. Okay, so finally I can say that 10th statement is actually false. Now let's see the 11th statement. That's our last statement. The 11th statement is saying for all x, and inside what we have? Inside we have qx, means if q is true, then there exists a y, rxy is true. Okay, what this is saying? There is a universal quantifier. So this statement is saying that for every element in the domain, if q is true, then there exists a y such that rxy will be true. If q is true, then we have to worry about it. Okay, this is a universal quantifier. So for every element, actually for every element in the domain, we are saying that if q is true, then this would happen. Now you can notice, if I take x equal to 1 comma 3, then q will be false. False implies anything will be true. So I only have to check 2 comma 4. For 2 comma 4, q is true. This q is true. Now if I take x equal to 2, then can I say there exists a y such that r2y will be true? Yes, y equal to 1 will work. r21, that is true. What about x equal to 4? If I take x equal to 4, is there any y such that r4y will be true? r4y will be true. Yes, 1 will work. Is this clear? See, very simple. Here the domain, you know that domain is 1 2 3 4. This is the domain. Okay, and let's, for a moment, let me call this whole thing, let me call it alpha. Okay, so for this alpha, you can see, if I take 1 or 3, then alpha will be true. Okay, because q will be false. False implies anything will be true. Okay, so you can see alpha is true. What about 2? If I take 2, then alpha will be true. Who is the y? If I take x equal to 2, then q2 will be true. Q2 is true, implies there exists a y such that r2y is true. So 1 will work, y equal to 1 will work. If I take x equal to 4, then also alpha is true. Which y will work? If I take x equal to 4, then q4 is true. there exists a y such that R for y is true. Yes, 3 will work, y equal to 3 will work, or y equal to 1 will work. Okay. So very simple, you can see that for every element in the domain, this alpha is true. So I can say universal quantifier will become true. So this 11th, this actually will be true. So that's it. This is the complete analysis of this question. I hope you understood. This is a beautiful question. Basically, the complete revision of first order logic we have done through this question. We have seen nested quantifiers. We have seen existential quantifier with implication. That is a tricky part. Okay. Some good questions we have seen. So basically, this, I hope you understood everything in this question. The complete analysis of this question, did you understand? Let me know. This is a beautiful question. Through this question, the complete revision of first order logic we have done. These are the answers. You can check it out. Okay, you can see. So this is a question taken from MIT. I hope you understood the complete analysis. I hope you loved this question. Let me know your opinion about this question in the comments you can put. Okay. Let's solve this GATE DA 2026 question. Assume that a creative person will succeed if the person is also disciplined, but will not succeed otherwise. This is the statement given to us. Now, consider the following statements. These are the three statements. Which of the following options is correct? Basically, both 1, 2 are true, means these are true. Only 2 is true, like that. These four options we have. Okay. Now, before we solve this question, I will take one analogy and then we will understand this statement. Notice one thing, if you read this statement, read this and tell me this statement is actually talking about which type of people. Very simple. Is it talking about all the people or is it talking about only a specific type of people? See, read this statement. Assume that a creative person will succeed if the creative person is also disciplined, but otherwise that creative person will not succeed. Do you agree that this statement is actually only focusing about the creative people? This statement is making a claim about the creative people only. This statement is not saying anything about the non creative people. Is this clear? Very important thing that you read this statement. This statement is making a claim for only creative people. This statement is not saying anything about the non creative people. The non creative people can do anything they want, they can be anything they want. But this statement is saying that a creative person, which type of person? A creative person will succeed if the person, what is the meaning of the person here? The person means creative person. So remember, a creative person will succeed if the creative person is also disciplined, otherwise the creative person will not succeed. It's all about creative person. This statement is only making a claim only about the creative people. It is not saying anything about the non creative people. Now let me take another example to understand what I am saying. Consider this example. It will be more intuitive to you. You will feel more connected with this statement. So let's see. A gate aspirant will succeed if the gate aspirant is also consistent, but otherwise the gate aspirant will not succeed. Now you tell me, this statement, if I speak, I am a gate teacher, if I speak this statement, am I only focusing on the gate aspirant or am I making a statement for all the students in the entire world? I am only focusing on the gate aspirants. Yes or no? Okay, so remember, here I am saying a gate aspirant will succeed. My focus is only gate aspirants. I am giving some gyan to the gate aspirants, that I am saying that a gate aspirant will succeed if the gate aspirant is also consistent, otherwise the gate aspirant will not succeed. So how to convert this into propositional logic? What you will say? There are two ways to write it. The first thing you can say that, see, a gate aspirant, I am talking only about the gate aspirant. I am saying that if you are a gate aspirant, then you will succeed if you are also consistent. Means if you are a gate aspirant, and you are consistent, then you will succeed. Agree? Okay, because read the first statement. Read the first statement. I'm saying a gate aspirant will succeed if the aspirant is also consistent. Means if you are gate aspirant also consistent, then you will succeed. This is the first line. This is the first line. But means and. But means and. We already know. But means and. Okay, and what else I am saying? I am saying that otherwise the gate aspirant will not succeed. What is the meaning of otherwise? Otherwise means if the gate aspirant is not consistent, then the gate aspirant will not succeed. Means if you are a gate aspirant, if you are a gate aspirant and you are not consistent, if you are a gate aspirant and you are not consistent, then you will not succeed. This is how I can write it. I hope you understood. Please tell me, did you understand? Very simple, remember, read this statement. We are making a claim only for the gate aspirants that if you are a gate aspirant as well as consistent, then you will succeed. Gate and consistent means succeed. But means and otherwise you will not succeed. Otherwise means for the gate aspirant, I'm saying, for the gate aspirant, I'm saying that if you are gate aspirant and not consistent, gate aspirant and not consistent, then you will not succeed. This is the given statement. This is how I can write the given statement. There is another way to write it. What is the another way? Notice one thing. I am only making a claim about the gate aspirants. So I can say that if you are a gate aspirant, then I am saying something to you. Like this, I can write. Do you agree with me? I can say that if you are a gate aspirant, if you are a gate aspirant, then something I am making a claim about you. If you are a gate aspirant, then something I am telling, something I am saying about you. So now, if you are a gate aspirant, then what I am saying? I am saying that if you are consistent, then you will succeed. Otherwise, you will not succeed. Means if you are consistent, then you will succeed. If you are not consistent, then you will not succeed. It's like this. If you are consistent, then you will succeed. And if you are not consistent, then you will not succeed. Okay. Now, what is this? This is C implies S and C bar implies S bar. I can also write it C by implication S. Yes or no? This same thing, I can also say that this is basically C by implication S. Okay, agree? So I can say that if you are a gate aspirant, then I'm saying something about you. What I'm saying that if you are consistent, then you will succeed. If you are not consistent, then you will not succeed. Means if you are a gate aspirant, then this is the claim I'm making. I'm making this claim that your success fully depends on your consistency. That's it. Okay, I hope you understood. So these are the three ways to write this statement. Okay, now let's come back to this gate DA 2026 question. What I'm saying that for creative people, I'm saying a creative person will succeed if the creative person is disciplined. Otherwise, the creative person will not succeed. Here we are making a claim only for the creative person. We are not saying anything about the non creative people. If you are non creative, then you may succeed, you may not succeed, you may be disciplined, you may not be disciplined. I don't care. I am not making any claim about the non creative people. I am not addressing the non creative people. We are only addressing the creative people. A creative person will succeed if the creative person is disciplined. Otherwise, the creative person will not succeed. Okay, so how I can write it? I can write it that if you are creative and you are disciplined, then you will succeed. But means and if you are creative, because I'm only talking about creative people, if you are creative but you are not disciplined, if you are creative and not disciplined, then you will not succeed. So this is how I can write it. What is another way to write it? Another way is I'm making a claim only for the creative people. So if you are creative, then I'm saying something about you. Now what I'm saying about you? I'm saying that if you are creative, then what I'm saying that if you are disciplined, then you will succeed. If you are not disciplined, then you will not succeed. Now this whole thing I can write D by implication S. So finally, I can say that if you are creative, then your success fully depends on your discipline. If you are disciplined, then successful. Not disciplined means not successful. So like this. I hope you understood. You can notice all of them are equivalent. You can check it out. Okay. If you simplify this, you will get the same thing. Okay. Let me show you. If you want, you can see. Let me show you that on one side we have written this expression that if you are creative and disciplined, then you will succeed. And if you are creative and not disciplined, then you will not succeed. On one side, this is the expression. On another side, our expression is if you are creative, then what I'm saying that success fully depends on discipline. Okay, like this. Now you can see both are actually equivalent. Let's do the simplification. Here you can see this is P implies Q, so it will be P bar or Q. Okay, so what will be P bar? You can see it will be like this: C and D whole bar or S, and C and D bar whole bar or S bar. Okay, what I will get? I will get C bar or D bar or S, and C bar or D or S bar. Okay, now if you simplify this, what you will get? You will get C bar means C bar, C bar, that means C bar D and C bar S bar, C bar D or C bar S bar, or you can see D with C bar, so that will be again C bar D, sorry, D bar with C bar, so that will be C bar D bar, D bar with D, that will be false, that will be 0, D bar S bar. Okay, or S C bar or S D or SS bar, that will be false. Okay, so you can see now you can apply the absorption property here. What was the absorption property? Do you remember the absorption property? Let me write it here. What was the absorption law? Absorption law is saying that if you have like alpha or alpha beta, then you can write it alpha. Yes or no? If you have alpha or alpha beta, that you can replace with alpha. So here you can see we have C bar. This is alpha. C bar is the alpha. Here also alpha. Here also alpha. Here also alpha. Here also alpha. Okay, so all these things I can simply replace with C bar. What else I have? I have SD or S bar D bar. Okay, so this is what I got. Now let's see. If I simplify this expression, what I will get? I will get C bar or, and you already know D by implication S. I can write it D bar S bar or DS. Both are same. You can see this expression and this expression both are same. Yes or no? This expression, both are same. Okay, so that's it. I hope you understood. Basically, I'm saying that the given statement, you can either write like this, or you can write like this, or you can write like this. Okay, I hope you understood. Now, let's come back to our GATE DA 2026 question. So here you can see these three statements are given to us, and the question is asking now consider the following statements. We need to find which of them is it true. Okay, so you can clearly see the second is definitely true. If you are creative, then this is if creative, then your success fully depends on your discipline. Yes or no? So this second is definitely correct. Okay, now notice the first and third we have to check. Basically, this is the given information. If this information is given to you, then we need to see these two are inferred by this information or not. Okay, please understand. This is the given information. Now from this given information we need to find these three are true or not. So means from this given information, can we infer these three? So the second we can definitely infer. Actually, the second is exactly same as the given information. The second statement is exactly same as the given information. But we have to check that from the given information, can we infer this first comma third? Okay. Remember, the question is not asking that this given statement is equivalent to which of them. Okay, the second is actually equivalent to the given information. This second expression, this is equivalent to the given statement, but the question is simply saying that this is what you assume. This statement you assume, and after assuming this statement, you find which of these expression is true. So actually, from this information, we have to check that what we can infer from this given information. This is what we have to check. I hope you understood. Definitely, second statement we can infer because this is equivalent to the given information. So I can say that option D I can eliminate because second is definitely true. Okay, second is actually true. But what about the first comma third? That we have to check. Okay, so let's check the first comma third. So first, the given information, given or assumed correct statement. What is the assumed correct statement? The assumed correct statement is, if you are creative, then your success fully depends on your discipline. This is the given statement. Okay, and what is option A comma B? Sorry, what is statement 1 comma third? Statement 1 is, if you are creative and successful, by implication disciplined. Means creative and successful, by implication disciplined. Notice one thing, if you think logically, intuitively, then this does not make any sense. From the given statement, we are saying that if you are creative, then something, we are making a claim about you. The given statement is making a claim about the creative people. But look at the first statement. This first statement is making a claim about disciplined people. The given statement is making a claim about creative people. The first statement is making a claim about disciplined people, because we are saying that if you are disciplined, then you will automatically be creative and successful. If you are not disciplined, then it will not happen. Okay, so intuitively, if you think, then notice one thing, the given statement is making a claim about the creative people, and the statement one is making a claim about the disciplined people. So definitely there is nothing here, yes or no? Definitely from this we cannot infer this. Okay, but there is another way, let me tell you. Okay, if you did not understand this logical understanding, then also we can easily see. Basically, we have to check that if this is true, then can I say this definitely will be true? Okay, so can you make this given statement true and this expression one false? Can you do that? Notice, when this given statement will be true. Okay, see, the given statement, the given or assumed statement, the given or assumed statement, what is that? That is C implies D by implication S. Now tell me when this will be true. So you can see when it will be true. Here on one side, let me write CDS. So you can see that if I make C false, then anything I can take here, then this given statement will become what? This given statement will become true. Okay. Can I make this first statement, first expression false? C and S. Okay. See, notice I'm saying if I make C false, then the given statement will become true. In this situation, can I make this expression one false? Yes, I can make expression one false. For example, what I can do? I can make D true and I can make S true. Okay. In this situation, notice in this situation, the given statement will be true, but the expression one, that will be false. The expression one will be false. Okay. Is this clear? Let me know. I hope you understood. So finally, I can say that from this, I cannot infer this. Okay. It is basically that if this is true, then we cannot say that this will be true. Okay. From this information, we we cannot infer this information. Okay, I hope you understood this. Very simple point. Okay, this is the counter example. You can take C false, you can take D true, C false. So yes, this first expression will be false and the given statement will be true. Okay, let's see the third one. Third one, first you simplify this third one. Okay, here you can see we have C by implication, and inside what we have? First you simplify this. Here you have D implies S, so that will be D bar or S bar. Okay, D implies S, that will be D bar or S bar. So here it will be one true, it will be true, S or S bar will be true or anything that will be true. So you can see this will be actually true. So finally this third statement, what it becomes? This becomes C by implication true. What is C by implication true? I can write it C T bar or C bar T. Okay, and it will basically become C bar. Sorry, sorry. This C by implication T, what I can write it? I can write it CT or C bar T bar. So it will basically become C. Okay, so basically the third statement is same as C. Okay, remember the third expression, that is basically C only. Okay, so the third expression is only C. Again, you can notice this is the given information. Given information is saying that if you are creative, then something. And the third statement is saying you are creative. So definitely from this we cannot infer this. Correct? Because the given statement is saying that if you are creative, then something. But the third statement is saying directly saying you are creative. So of course from this information we cannot infer this information. But still what you can do? Can you make this first statement, sorry, can you make this given statement true and the third expression false? Yes, I can do that. Okay, what I can do? I can take C, D, S. What I can do? Make C false, anything D, anything S. Now here what will happen? The given statement will become true and this third expression will become false. Okay, so finally I can say that from this given information we cannot infer this third expression. Okay, so that's it. So this is not true, this is not true, only second is true. Yes, so the answer will be option B. I hope you understood. This is the complete analysis of this GATE DA 2026 question. Okay, here only one thing you have to understand, that the given statement that we have to assume true, this given statement is only making a claim about the creative people. It is only saying that what will happen if you are creative. But if you are not creative, then nothing is said. We are not making any claim about non creative people. Okay, so means if you are creative, then what will happen? Then your success fully depends on discipline. If you are disciplined, then successful. Not disciplined, then not successful. Okay, so this second expression, this is equivalent to the given statement, and the question is basically saying that if you assume this information to be true, then what we can infer? So we can see that only the second expression we can infer, nothing else we can infer. This is the complete analysis of GATE DA 2026 question. So please let me know, did you understand this complete analysis? Let me know in the comments as well. Okay, let's solve this question from predicate logic or first order logic. For the universe of all integers, the domain, the universe is all integers. Let Px, Qx, Rx, Sx, Tx be the following statements. These predicates are given to us. Write the following statements in symbolic form. Means these English statements we have to convert into predicate logic expression. Okay, so let's solve it. Let's see the first one. At least one integer is even. Remember, the universe is already integers. The universe is already set of all integers. So this statement A, this is saying at least one integer is even. But the universe is set of all integers, so I can say that at least one element in the domain is even. Tell me which of these predicate is talking about even. Let me know which of these predicates is talking about even. The P predicate, Px means x is even. So this statement A, we can say at least one integer is even, but the domain is set of all integers. So I can say that at least one element in the domain is even. Okay, so I can directly say at least one element in the domain, there exists x in the domain such that x is even. X is even means Px. That's it. So this is part A. We have done it. Let's see the next part. There exists a positive integer that is even. Here there are two things. The first thing is positive integer. The second thing is even. For even, what is the predicate? P predicate is for even. For positive integer, what is the predicate? Integers are the domain. So tell me, for positive, what is the predicate? See, for positive, what is the predicate? For even, what is the predicate? You can see this as this is for positive. Positive means greater than 0. Remember, 0 is neither positive nor negative. Please understand this. Please understand that 0 neither positive nor negative. 0 is neither positive nor negative. Okay. Positive means greater than 0. Negative means less than 0. Negative means less than 0. 0 is neither positive nor negative. 0 is even, but 0 is neither positive nor negative. Okay, remember 0 is even, but it is not positive. Don't say that it is positive. Not positive. It is neither positive nor negative. So here you can see that positive means the predicate is S and even means the predicate is P. Okay, and what about integer? That is the domain. That is the domain. Okay, so I can say there exists an integer. That means there exists an element in the domain. There exists an element in the domain. Or I can say there exists an integer which has two properties. It is positive as well as it is even. There exists an element in the domain, or I can say there exists an integer such that it is positive and it is even. So finally I can say there exists a positive even integer. Okay, very simple. Let's see the next. Let's see the C. What about C? If x is even, then x is not divisible by 5. Tell me one thing. This type of statement, when we speak, are we talking about a particular x, or are we talking about all x, or are we talking about some x? Read this statement and tell me. In your real life, in your daily life, when you speak this statement, if x is even, then it will happen. Are you talking about universal quantification or existential quantification or specific y? Let me know. Or specific x? Let me know. Yes, this statement is basically universal quantification. Please understand something important. It's very intuitive. In your day to day life, whenever you want to say, for example, if you want to say that all, for example, if you want to say cats are cute, okay, if you say cats are cute, then what it actually means? Tell me, in your daily life, if you say that if it is a cat, it is cute. If it is a cat, it is cute. Now you tell me, if someone speaks this statement, a person X is speaking this statement, or maybe a person P is speaking this statement, then what this person P actually means? What is the actual meaning? The actual meaning is, remember, universal quantification is hidden here. Do you agree with me? Let me know. Universal quantification is hidden. Basically, this person P want to say that for all the people I am saying, for all the elements, I am saying that if it is a cat, then it is cute. It's like in my daily life, if I say cats are cute, then does it mean some cats are cute or all cats are cute? It's like this. If I say cats are cute, This is what I speak. Now tell me, just tell me what is hidden here. By default, what is hidden here? All is hidden, all is implicit, or some is implicit. This is what I am speaking. This is what I am speaking. This is what I spoke. Now tell me, what is implicit? Universal quantification or existential quantification? The answer is universal quantification. When we say cats are cute, we are basically saying that all the cats are cute. Okay, so remember, in our daily life or day to day life also, the universal quantification is hidden basically. That is implicit. Okay, so here also it is very intuitive that if you read this statement C, it is saying if x is even, then x is not divisible by 5. It simply means we are talking about all the x. Basically, for all the integers, we are saying that if it is even, then it is not divisible by 5. This is what we are saying. This claim we are making. This can be a false claim, this can be a true claim. I don't care. We don't care about the truth value of this claim. We just need to convert this claim into first order logic expression. Okay. So here, please understand that in this statement, also in this statement, the universal quantification is implicit, or I can say hidden. Okay, the universal quantification is implicit. Is implicit. Okay, I hope you understood this. Here also in this statement F, we are saying if x is even and x is perfect square, then x is divisible by 4. What we are basically saying, we are saying that for all the integers x, we are saying if it is even and perfect square, then it is divisible by 4. So here also in this statement F also, universal quantification is implicit, or I can say hidden. In this statement C also, universal quantification is implicit or hidden. Okay, now you tell me, for this statement C, if x is even, then x is not divisible by 5. And here the universal quantification is hidden, means for all the x we are saying, for all the integers we are saying, what we are saying, we are saying that for all the integers, for all the elements in the domain, we are saying that if it is even, even means p, if it is even, if it is even, then x is not divisible by 5. And you can see r means x is divisible by 5, so negation r. So I can say negation rx. Okay, that's it. I hope you understood. So this is the important point, that this universal quantification, this was implicit. This was implicit, or I can say this was hidden. In our day to day life, in our daily life also, the universal quantification, we basically just, we we use it implicitly. We don't actually say, we don't say that all the cats are cute. We simply say cats are cute in our conversation. Okay, but when I say cats are cute, then I am actually talking about universal quantification. I am saying that all the cats are cute. Okay, so the universal quantification is basically, it is actually implicit in our day to day life, in our daily life also. Okay, now what about the next statement D? Let's see how to write D. In the D, we are saying no even integer is divisible by 5. Okay, so what I can write it, no even integer is divisible by 5. There are two ways to write it. Either I can say that there does not exist any even integer that is divisible by 5. I can say there does not exist. There does not exist. What this means? This means there does not exist. There does not exist. Or I can say there is no element x such that. There is no element x such that. This is what it means. Okay. So remember, we are saying there is no integer x such that it is even and divisible by 5, because we are saying no even integer is divisible by 5. So we are basically saying that there does not exist any integer which is even and divisible by 5. Even means p, and divisible by 5, that means R. So this is how I can write it. Okay, this is one way to write. What is another way to write? Remember, basically for all the elements we are making a claim. What is the claim we are making for all the elements? Please understand. For all the elements we are making a claim. Tell me, for every integer, for every element in the domain, which claim we are making? We are making a claim that if it is even, then it is not divisible by 5. If it is even, then it is not divisible by 5. Yes or no? Because this statement D, I can rewrite. This statement D, I can say that for all the integers, I am saying if it is even, then it is not divisible by 5. Yes or no? No even integer is divisible by 5. It means that for all for all integers, for all integers, we are saying that if it is even, if it is even, it is not divisible by 5. It is not divisible by 5. Okay. So this is what we have written here, that for every element in the domain we are speaking, we are making a claim. What claim we are making? We are making a claim that if it is even, then it is not divisible by 5. Okay. Basically, C comma D are basically same if you notice. Okay, C comma D, if you notice, they are basically same. Okay. Now let's see the next one. Let's see E. There exists an even integer that is divisible by 5. This is very easy. Okay. So this E you can easily write. E will be there exists an integer which is even and divisible by 5. Okay. Divisible by 5, that means Rx. Okay. So very simple. What about F? In F also universal quantification implicit. Yes or no? Universal quantification is implicit. So we are saying that for all the elements, we are saying, we are making a claim. For all the integers, we are saying that if it is even and perfect square, even means P and perfect square means T. Okay. If it is even and perfect square, then it is divisible by 4. Divisible by 4, that means QX. Okay, that's it. So here you have to understand that this is implicit. Okay. Universal quantification is usually implicit. In our day-to-day life also, usually the universal quantification is implicit. Okay. So that's it. I hope you understood. Very simple. So all these from A to F, did you understand? Let me know. Tell me the answer for this question. Determine whether each of the following conditional statements is true or false. Conditional statements are given to you. Remember, P implies Q is true if P is false or Q is true. P implies Q is false only in one case, when P is true and Q is false. Okay, so here you can see. What about A? If 1 plus 1 equal to 2, this is true, right? Then 2 plus 2 equal to 5. So this is false. True implies false. What is that? If then means this implies this. So true implies false. That is basically false. Okay, so this is actually false, I can say. So this is false. What about B? If 1 plus 1 is 3, this is false. False implies anything. False implies anything. That is true. So this actually is true. If monkeys can fly, again if then monkeys can fly, that is false. False implies anything. False implies anything. That will be true. So this is actually true. If 1 plus 1 is equal to 2, that is true. Dogs can fly, that is false. So true implies false, that is false. So this actually will be false. Okay. So quite easy. Let's solve this question. Write the contrapositive, converse, inverse of the statement. If P is a square, then P is a rectangle. So let's see here. You already know that if you have a conditional statement, if you have a given conditional statement, if we have a given conditional statement P implies Q, then for this given conditional statement, what will be the converse, what will be the inverse, what will be the contrapositive? So let me know what will be the converse of this. So if the given conditional statement is if P then Q, then the converse will be if Q then P. What will be the inverse? Inverse will be the given conditional statement is if P then Q. The inverse will be if not P then not Q. If not P then not Q. And what will be the contrapositive? The contrapositive will be if not Q then not P. Okay. And remember one more thing, that any conditional statement is equivalent to its contrapositive. Okay. So you can see that P implies Q. This is equivalent to negation Q implies negation P. Any conditional statement is equivalent to its contrapositive. So here the given statement, what is the given statement? The given statement is that if P is a square, then it is rectangle. The given statement is square implies rectangle. Okay. Now tell me, this is the given statement. So for this given statement, what will be the converse? What will be the converse? Converse means if it is rectangle, then it is square. Okay. If it is rectangle, then it is square. Also remember the question is saying, are all the statements true? The given statement is true or false? Can anyone tell me? In the geometry, the given statement, if P is a square, then it is a rectangle. Square implies rectangle. Yes, this is actually true in the geometry, correct? True in geometry. This is actually true in geometry. Okay. What about this converse? Converse means if it is rectangle, then it is square. This is actually false. Rectangle does not mean it is square. Rectangle may or may not be square. Okay, yes or no? What about the inverse? What about inverse? So the given statement is square implies rectangle. The inverse will be if it is not square, then it is not rectangle. Okay, if it is not square, I can say that if it is not square, then it is not rectangle. So tell me, if something is not square, then can I say it will be not rectangle? If a shape is not square, then can I guarantee it will be not rectangle? No, it may or may not be rectangle. So it is also false. Next, what about the contrapositive? The contrapositive will be if P is not rectangle, then it is not a square. Okay. So for this square implies rectangle, the contrapositive will be not rectangle, then not square. Okay. So it will be rectangle, not rectangle. If P is not rectangle, then it is not a square. Is this statement true in the geometry? That if a shape is not rectangle, then definitely it is not a square. Yes, this statement is true. Because we already know every square is rectangle. So if a shape is not rectangle, then it is not a square. Okay. Very simple. Here also you can see that given statement is actually equivalent to the contrapositive. But the given statement is not equivalent to the converse. The given statement is not equivalent to the inverse. Okay, so very simple. I hope you understood. These questions 5,6, please pause the video and solve them. Put your answer in the comments. Then you play this video. Take this, take these question 5,6 as homework. But of course, I will solve it now. But pause the video, solve these questions, and put your answer in the comments. Let's see question number 5. Question number 5 is saying, show that this expression is tautology using equivalence laws. So expression is given to us, that is P or Q, P or Q. For simplicity, I can write it plus. This plus simply means or. Okay, I told you that this disjunction, what are the disjunction symbols? These are either you can write like this or you can write like this. Okay, both are same. So you can see P or Q. And what about the conjunction symbols? Conjunction symbols are either like this symbol, or you can this symbol, or you can simply write it PQ. Okay, so I can say it will be like P or Q and negation P or R, negation P or R, and Q or R, and Q or R. Okay, so let's see what we can do here. We can just multiply them. Basically, it's like we can apply the distributive property, or basically we can do this type of multiplication, I can say. So this P bar, that will be false. Okay, P bar, that will be false. False or anything that will be false, or alpha, that is alpha. False or alpha, that is alpha. So I can say it will be basically, it's like PR. Okay, here this is what I'm doing. So it will be PR or P bar Q or QR. Okay, with this we have Q or R. Okay, so let's see here. Now again the same thing. Q with PR, that will be PQR. Q with P bar Q, that will be P bar Q. Q with QR, that will be QR. Or R with PR, that will be PR. R with P bar Q, that will be P bar QR. R with QR, that will be QR. Okay, so you can see here. Notice one more thing, that this absorption law we know. Absorption law, absorption rule, that basically says that if you have alpha or alpha beta, that is equivalent to alpha. So notice one thing here. It's like QR or QR, that is basically QR. Okay. Now this QR, let's call it alpha. Here also you have QR. So it's like alpha or alpha beta, that I can simply write as alpha. So remember, I can simply write it as QR. Okay, these things have become QR. Next you can see what we have. We have P bar Q or PR or P bar QR. Okay, so here what I can do, here I can take here P bar Q, P bar QR. Okay, here also I can apply the absorption rule. Notice P bar Q, P bar QR. Let's call it alpha. P bar Q, let's call it alpha. So P bar Q is alpha. Alpha or alpha R. So you can see alpha or alpha beta, that is alpha. So here you can see from here also it will become P bar Q. Or what else is there? There is PR. Okay. Next, you can see I can take here what the question is saying. Show that this is a tautology using equivalence laws. I think this question is actually wrong, because actually it will not be a tautology. You can see we got this expression. If you further simplify it, you can apply the consensus theorem. Okay, see what is the consensus theorem. Let me tell you. So there is a theorem, consensus. This you will study in the digital logic also. Consensus theorem. In the digital logic, actually, we study this in the Boolean algebra. Consensus theorem. What this theorem basically says, it's like happy and sad property. Okay, just to remember, it's like happy sad property. What I mean that this consensus theorem says that it's like this, that x y or x bar z, x y or x bar z or y z, this you can simplify and you can remove this y z and you can simply write it x y or x bar z. Okay, basically why I'm calling it happy sad property, because here you can focus on x. It's like in the happy times of x, y was there with x. In the sad times of x, z is there with x. And here y comma z, they are doing some conspiracy against x. Okay, it's like this is the happy times of x, happy x. Okay, it's like here sad x. So in the happy times of x, y is there with x. In the sad times of x, z is there with x. And here these two people, y comma z, they are doing conspiracy against x. Okay, means when there is no x, then these people are together. Okay, so these conspiracy people you can remove and you can simply write it like this. Anyway, this is just to remember. But the point is, of course, you can prove it using the by case method. You can make two cases, x true, x false, and then you can easily see this expression LHS will be equivalent to RHS. Okay, so the point is, this is conspiracy. Okay, so this is the consensus theorem. Using this theorem, basically you can simplify this type of expression to this type of expression. Okay, I hope you understood happy sad property. This is how you can remember this property. And remember, the proof is very easy. Let me give this proof as a homework. Okay, proof, please take it as a homework. Or what you do, you apply the by case method. Homework, use by case method. Okay, now, so you can see further, if you want to simplify this, then what you will get, focus on p. In the happy times of p, here you have happy p, here we have happy p. Okay, here we have sad p. So in the happy times of p, r is there. In the sad times of p, q is there. Here this q comma r, when p is not there, then q comma r are together, they are doing some conspiracy. Okay, so you can simplify this and you can remove this conspiracy people. Okay, and finally you will get p bar q or pr. The point is, you cannot further simplify. This is the final, I can say, most simplified expression. This is the most simplified. I cannot further simplify. That is the point. So you can see, this is definitely not tautology. It is actually contingency. You can make it true, you can make it false. Okay, yes or no? So let me tell you that this is actually not tautology. This is actually contingency. Okay, you can make it true, you can make it false. For example, how can I make it true, how can I make it false? What we got p bar q or pr. Okay, you can see, I can make it true, I can make it false. When it will be true? True when I take p true r true. I can take p true r true, this will become true. And when it will be false, I can make it false as well. When it will be false, it will be false when I take r false. What I do? P you can take anything, p you can take true. The point is, you make q false, you make r false. Okay, so I can make it true, I can make it false. So finally I can say that it is actually a contingency. Okay, very simple. So remember, it will actually be a contingency. Okay. The question number 6. Use truth table to establish whether the following statement forms a tautology, contradiction, or contingency. This is the statement. Actually, truth table is a dumb method. Don't use truth table. Use by case method or use the simplification method. Okay. Don't use truth table. Truth table is a dumb method for the gate exam. So don't use the truth table method. What you do, use by case or use simplification. Okay, so either you use simplification or you use by case. Means either you use the rules, the logical laws you use, or you use the by case method. Okay, let me solve this question using by case method. Let me see whether this expression is tautology, contingency, contradiction. So let me see what we have. Question number 6. The expression is q and r and p bar or q and r, qr. Okay, and p bar and q, and p bar and q, p bar and q, with this whole thing and q bar. This is actually very simple question. This whole thing q bar. Okay, that's it. Actually, this q bar, this will become false. The whole thing actually will become false. Okay, so finally it will become false. And if any expression is always false, then it is contradiction. Yes or no? Okay, so basically I can say that basically this expression is contradiction. Okay, that's it. So remember, the final answer will be contradiction. Okay, so that's it. So question 5, 6, these are also completed. So that's it. In this session, we have done some standard questions. I've taken some very good questions from MIT and other top universities. I hope you loved this session. I hope you enjoyed and I hope you understood each and every question that we have done in this session. Okay. Is there any doubt? Let me know. Did you understand the complete analysis of each question? Some some very good question we have taken from MIT. Also, gate DA question we have done. So I hope you enjoyed and I hope you understood everything in this session. Okay. Thank you, everyone. Please share your feedback in the comments. Thank you.